We are going to study about the generalized circuit constants of transmission line. What will be the model which we discussed, that is short transmission line, medium and long transmission line. Now how to simplify the calculation using the generalized circuit constant, that we are going to see. So the generalized circuit constants are, there are four parameters are there. There are A, B, C and D are the parameters. So here you see that we'll be using two equations. One is Vs is equal to AVR plus VAR and Is is equal to CVR plus DAR. Using these two equations only, we are going to find the ABCD constants for various set of transmission line. So here A and D have no constants. There is no unit for A and D. The unit of B is ohm and unit of C is mho. So these are the parameters we discuss. Coming to the ABCD parameters, always after forming the ABCD, we have to check that there are two conditions to be satisfied. There are two conditions to be satisfied: A equal to D and AD minus BC equal to 1. Okay? These are the conditions we have to satisfy, so that the corresponding parameters we can able to check. In the corresponding, see here, first for the short transmission line, for short transmission line, Is is equal to IR, Vs is equal to VR plus IR into Z. So here, how we are getting this equation mean, based on the current and voltage equation, we come across that we have to convert the each and every equations into this form. Vs is equal to AVR plus VAR, Is is equal to CVR plus VAR. In this form, we have to convert it. After converting that, compare with the short transmission line expression and then find what is the value of A, B, C coefficients. After by doing that, by comparing these two expressions, A equal to 1, B equal to Z, and C equal to 0, and D equal to 1. These are the expressions we are getting for short transmission line. Then, after this, if we go and check whether A equal to D, yes, that condition is satisfied, and then AD minus BC is equal to 1, and that condition also getting satisfied. After getting these things, now we can use this ABCD constant to find the voltage regulation and efficiency. Then coming to the medium transmission line, in medium transmission line, directly we are starting with nominal T method. The reason is, in nominal T method, in incandescent method, both the conditions are not satisfied. Even though A is equal to D there, that AD minus BC condition is not getting satisfied over there. So that is the reason we can't able to use or frame the ABCD constants for a incandescent method, in medium transmission line for incandescent method. Coming to the nominal T method, nominal T, you know the final expression, compare with that, this is the equivalent circuit for that. Compare the equations, and there you have to get A equal to D equal to 1 plus Y into Z by 2, and B equal to Z into 1 plus Y Z by 4, C is equal to Y. These are the expressions we are having. Then for nominal pi model, these are the expressions. Once again, using these things, we can able to find the voltage regulation and efficiency. Yes. Yeah, in long transmission line, already the equation is of the form of Vs equal to AVR plus VAR. AVR plus VAR. So that what happens means, if you compare these two, if you compare the A equal to D and B, AD minus BC equal to 1, all those equations, you are getting the expression for this. That is why we have we can able to use this long transmission line also. Yes. So these are some of the numericals which we are not going to discuss now. Just to apply how to find the corresponding voltage regulations and efficiency of the various cases, etc. Yeah. Next topic is, so far we discussed about the modeling of transmission line. The model, there are three models I said: short transmission line, long transmission line, and medium transmission line. In all these models are purpose of all these model is to find the efficiency or transmission efficiency and voltage regulations only. Okay. So with this, almost in long transmission line, using a rigorous method, we can able to find the regulation and efficiency which is almost closer to the theoretical line. Yes. Coming to the corona. So this is the important thing which is occurring in the system. The definition of corona is, there is a violet glow, hissing noise, and production of ozone gas. Why we need to worry about the corona? There are some advantage and as well as disadvantage in the corona. See, corona is due to ionization of air surrounding the conductor. An alternating potential difference is applied across two conductors whose spacing is large. As compared to the diameter, there is no apparent change. That means if there are two conductors operating at two different potential. In between that, air will act as the ionization medium. So what happens means, if the distance between, that is said to be D, if the distance between the two conductors or span distance If it is more when compared to the diameter of the conductor, then what happened means there is no apparent change in the conductor. So because of this, what happened means there is no occurrence of corona. But at the same time, because of some reason, because of some disturbance or practical reasons, we can't able to maintain always the span distances. Maybe in the turning of the street or somewhere you have to cross the road, etc. In that case, what you have to do is we can go for reducing the span distance. Definitely, if that is the case, the air which is between the two conductors will get ionized, and there is a possibility of corona. So this corona, when it is occurring, there are two different voltages are there. One is called critical disruptive voltage. Let us say your operating voltage is 11 kV. So up to 11 kV, there is no formation of corona. Maybe due to some reason, your voltage may be increased a little, maybe 12 kV or 12.5 kV like that. In that case, there is a possibility of corona. And the corresponding voltage where the corona starts occurring is called critical disruptive voltage, and the voltage at which it will be appearing is called visual critical disruptive voltage. There are two voltages are there. One is critical disruptive voltage, other one is visual critical disruptive voltage. You can see this. When the applied voltage exceeds a certain limit called critical disruptive voltage, the conductors are surrounded by a faint violet glow that is called as a corona. Okay. This phenomenon of violet glow, hissing noise, and production of ozone gas in an overhead line is called as corona. This will not occur in a cable. This is only the effect is only in the transmission. Yeah. For normal condition, this is the phenomenon behind the corona, how it is occurring, or how ionization happened, what happened to how this ionization process started, how the free electrons strike the neutral molecules and ionized, and how the process of corona is getting started. Yeah, these are the various factors which are affecting corona. If you see that there are 4 factors which are affecting the corona. The first one is the atmosphere. Yes, obviously because of the atmospheric climate condition, in stormy weather the number of ions is more than the normal, and such corona occurs at much less voltage. Even if you are saying that critical disruptive voltage, due to atmosphere, even at lesser voltage itself, there is a possibility of corona. The next one is the conductor shape. The shape of the conductor is the matter. Suppose if it is a polished surface, the occurrence of corona is somewhat less. If it is a rough surface, then the possibility is more like this. And spacing between the conductor. If the spacing between the conductor is more, as I said earlier in the previous slide, the occurrence of corona is less. If the spacing is less, then the occurrence is more, like this. The line voltage, line voltage greatly affected. If you go for higher voltages, there the possibility of corona is somewhat more. These are the various factors which are affecting the corona. And the main the thing is, there are 2 voltages are there. We need to find it. One is the critical disruptive voltage, other one is the visual critical disruptive voltage, which is represented by a symbol V suffix C. V suffix C is the critical disruptive voltage, where G naught R into ln of D by R is the formula to find it. Where G naught is called the potential gradient, and that is 30 kV per centimeter maximum. For a convention system, the G max value is 30 kV per centimeter. That is a value. If you want to convert that into RMS, then it is coming around 21.2 kV per RMS is the corresponding value. So that G naught you have to find it and substitute there to find the critical disruptive voltage. So here there are several factors we need to consider while finding the occurrence of corona voltage. So in that case, you have to go for del, where del is the air density factor. And the factors we discussed that there are some 4 factors which will cause the corona occurrence much sooner, like that. So in here also Vc is G naught and the del R into ln of dVr. Del is 3.92 B by 273 plus T. Using that formula, we can able to find the corresponding value. That is the critical disruptive voltage. Then using that formula, the surface also we discussed. The surface parameter is m naught, where m naught is equal to 1 for a polished surface. More the dirty surface or more the corresponding thing, the corresponding value is less. So like that I can say. So that is the critical disruptive voltage. The visual critical voltage is a voltage slightly more than the critical disruptive voltage. Visual critical voltage is a voltage which is slightly more than the critical disruptive voltage. So this is once again the formula for finding the visual critical voltage. Both the voltages are required to design the transmission line so that there is a less possibility of corona occurrence. Yes. Coming to the power loss. Before that, is there any drawback due to occurrence of corona? Means yes, there is a power loss. There is a power loss due to corona. since there is a power loss in the transmission line unnecessarily due to corona, we need to see that how the possibility or the frequency of occurrence of corona as much as possible we have to reduce it. So this is the formula. This is an empirical formulas. All these three formulas, visual critical, critical disruptive, and power formulas, no need to go for the derivation. All these formulas are empirical formulas. Just we have to take it as it is. These formulas are based on their experience and practice of the power engineers. It was that. Yes. Then a drawback of corona, just as we discussed, there is a loss of energy. Ozone is produced by corona may cause corrosion of the conductor itself. And the current drawn by the line, since there is an arcing formed, the current drawn by the corona is non-sinusoidal, and non-sinusoidal voltage drop occurs in the transmission line. This may cause some inductive interference related to some communication line. If it is there nearby, it will be happening. But here I didn't mention about the advantage of corona, but even though there are some advantages, what is the advantage of corona mean? Let us say there is a lighting strike in the transmission line. That lighting strike, what happen mean, because of that more amount of voltage, if it is a 11 kV transmission line or 20 kV primary distribution line, in that case what happen mean, there is a huge voltage will be traveled in the form of traveling wave, and that voltage will form a corona, and that traveling waveform will go and hit the primary winding of the transformer. Suppose before this, if corona get formed, the entire traveling wave as well as the current of due to corona will be dissipated in the form of arc, so that the intensity or the amount of or magnitude of voltage which is hitting the primary winding of the transformer is reduced. In that way, we can able to safeguard the transformer primary winding. In that way, we can able to assume that it is an advantage of a corona. Then, how to reduce the corona, or what are the various ways to reduce the corona? In the sense, there are two ways only. By increasing the conductor size, and there are obviously we have to see that once if I am saying that it is increasing the conductor size, we have to see in the other direction, is it economically feasible, or that Kelvin's law is getting satisfied. These are the things you have to see. Then by increasing the conductor spacing, the next one is by increasing the spacing between the conductor as greater as the diameter of the conductor. If you do that, the problem is once again the span distance increases. The amount of cost which we are spending for the transmission line increase, this will increase the overall cost of the transmission line. So once again, check the feasibility. All these things are coming under power system economics point of view. Yes, these are some of the numericals which is based on the corona that we have to see. And, there are something called the Ferranti effect in your transmission line. What is the Ferranti effect in the sense? The Ferranti effect is a rising voltage at the receiving end when compared to sending end at some particular condition. So, which causes that high voltage at the receiving end? Suppose if I am sending 11 kV in the primary or the sending end, if you go and measure after 10 km or 20 km, definitely the voltage will be less than that. If it is 11 here, it may be 10.5 kV, 5 kV. But there are some conditions where you are getting, if you send 11 kV at the sending end, if you go and measure the receiving end, it may be 11.2 or 11.3 kV. The reason behind that is called the Ferranti effect. This effect is due to lightly loaded transmission line, or if it is a new transmission line that if you are going to erect it. There are so many capacitors exist between the transmission line. Each and every capacitance will form a charging current. The charging current will support some amount of voltage and will be leading the voltages which you apply, so that these charging current, these are virtual capacitors in the transmission line which causes charging current, and that will increase the voltage at the receiving end. So that we have taken care. Power flow through the transmission line. To find the power flow in the transmission line, it's a bidirectional flow. Okay, like Vs is equal. These are two formulas. You know that Vs is AVR plus VIR, which is the equation of your generalized circuit constant. From there you have to derive it. Write the expression for PR plus JQR, where PR is the receiving end power, QR is the receiving end reactive power. If you find that, you are getting Vs into VR by B angle beta minus alpha minus AVR square by B angle beta minus alpha. Okay. So here we consider that alpha, betas are the constants coefficients or angle of the constants. A, B, C, D are the constants. A at an angle of alpha, B at an angle of beta. From there you have to consider. If you see this, Vs is the sending end voltage, VR is the receiving end voltage. Both these voltage should be a line value. But substituting that, both the values should be line value, and B is the equivalent impedance, which is normally in terms of ohm. Then if you divide that into real part and imaginary part of the previous expression, if you see this expression, if you find the real part of this and the reactive part of that, we have two expressions. One is for receiving at real power, other is the receiving at reactive power. You can see that if you operate with cosine term, it is the real power of the receiving power and reactive power of the receiving power. So from there we can able to draw the circle diagram to understand the various quantities. Yes. So the power circle diagram. This is an important topic to find the various. This is a graphical representation of the system. This is used to find the various parameters. Suppose there are using a circle diagram. The power circle diagram is a graphical representative and used to determine the capacity of VAR devices. VAR in the sense how much is the capacitance I have to use. Okay. Yes. Coming to the power flow in a transmission line, our aim is to find the various parameters. Suppose if I am saying that in a power circle diagram, we are going to discuss about the power circle diagram, where there are receiving end circle diagram and sending end circle diagrams are there. So to find the receiving end circle diagram, to find the receiving end parameters, we have to go for receiving end circle diagram. So here, what happened mean, suppose I want to find if I am sending this much of power, what is the condition to get maximum power at the receiving end, how to increase the maximum power, those things we can able to see. And based on these expressions, there are two equations I said. One is the receiving end power, other one is the receiving end real power, other one is the receiving end reactive power. Using these two expressions only, we are going to solve the circle diagram. So to solve the circle diagram, if you see that, to solve the circle diagram, so this is the circle diagram for the receiving end. First, you need to identify how much is the radius of the circle. To identify the radius, you see the expression Vs into Vr by B. That will give you the radius of the circle, and A into Vr square by B, that will give you the coordinate of the circle. A into Vr square by B is the coordinate, and how much angle it is tilted, since both are negative, both are value A minus R. See, this is minus A Vr square by B. If you operate with cos or sine, both are coming negative. That is why the center of the circle is here. Both are negative. Okay, that is the third quadrant. Then from there, at an angle of beta minus alpha from the negative x-axis, draw one line for a magnitude of A Vr square by B. A Vr square by B will give you the magnitude, and at an angle of beta minus alpha, so that will give you the corresponding value. So A Vr square by B, so that will give you the corresponding value over there. So here, this line that you have to identify. Then to find the radius of the circle, radius is Vs into Vr by B. To find the radius of the circle, what you have to do is use this operation Vs into Vr by B. From here, from the center of the circle, draw an arc for the radius Vs into Vr by B. Okay. Then after this is the first step. First step, you need to identify that what is the identify the center of the circle. To identify the center of the circle, so what you have to do is at an angle of beta minus alpha, draw one line whose magnitude is A Vr square B. Let us say A Vr square B, by substituting Vr, it should be a line value. After substituting that, if you are getting the value as A Vr square B as 500 megawatt, for example. If I assume 1 unit is equal to 100 megawatt, then 5 centimeter is the scale of an angle of beta minus alpha. I have to identify the center of the circle and draw one arc for the radius of Vs into Vr by B. So these are the things we have to do first. And after doing that, so what I have to do is, if suppose theta r is given, if I am going to deliver the load to the receiving end power at an angle of maybe 36.86, how I arrive at the angle in the sense, if the power factor is known, if the cos pi r is given as 0.8 or 0.9, from there you can find what is the value of pi r. Then after finding the pi r value, just at an angle of that, you just draw one line and find the operating point. So that operating point will give you the value of how much is the real power. If you see this, how much is the real power it can able to deliver, and how much is the reactive power you have to support to deliver that much of power. So these are the various cases. And other than that, there are another question that is it possible to find what is the maximum power I can able to deliver using these things. If that is the case, what I have to do is, see, from the center of the circle, you just draw one line which is parallel to the from the center of the circle, draw one parallel line with respect to x-axis that will touch the arc. Then, from this point, wherever it is touching the y-axis to the circumference of the circle, you just measure what is the distance. Then convert that into the power scale. If you do that, the corresponding number, the corresponding value which you are getting is the corresponding maximum power you can able to deliver. So this is the receiving end circle diagram. First step is you have to identify the center of the circle. The center of the circle, using this receiving power expression, you find the value of the second coefficient. There are two terms are there. The second term will give you the coordinates. So a VR square by b both are negative. That is why it's the third quadrant at an angle of beta minus alpha. And the first coefficient will give you that bs into VR by b will give you the radius of the circle. Using that, you have to form the circle. After forming the circles, next step is, after forming the circle, what you have to do is find the operating point in the arc so that corresponding how much the real power and reactive power we have to deliver. So for finding that, what I have to do is, you see that the corresponding from here, if you measure that on the x-axis value, that is your real power delivered for that much of mass per hour, and reactive power how much you have to supply. These two things we can able to find it. Other than this, there are something called critical angle. That angle also from here, from the center, at an angle of alpha, you draw one line. The distance between the reference line to the these two lines, that's NH line, will give you the corresponding angle called delta, and delta is called as critical angle. Yeah. Here max, you can able to use these formulas also. Beta minus delta is equal to 0. From there we can able to find it. So in that way, we can able to find, these are some of the diagrams to find how much the reactive power supplied, how much the real power supplied, etc. And case 2, here also you can see that. Next topic is a sag. What is mesh sag? If you are erecting a transmission line, this is the mechanical design of a transmission line. If you are going to erect the transmission line, there we have to consider this sag. That is an important thing which you have to consider when erecting the transmission line between two poles. Why? Because the amount of sag which you are going to keep between the two is based on a calculation that we are going to see now. And that will be very simple if it is a level support. That means both the towers are at equal height. If the level is different, then the corresponding calculation is somewhat tedious and you have to find the corresponding line sag. So here, the first diagram, if you see that there are A and B are the two supports. A and B are the two supports where present at equal distances. And so that if you see the shape of that, it is looking like a catenary shape. Okay. And the middle point is almost at the center of the circle. If the distance between the two span is 30 meters, the minimum point of the conductor is exactly at the middle, which is at 15 meters from either end. That is the first case. Then, here the definition of sag is the distance between the highest point of the tower and the lowest point of the conductor is called as sag. The difference in level between highest point of the tower and then to the lowest point of the conductor will give you the corresponding sag. The S is called sag. There are some places where, see the second case you can take, A and B are the two unequal level supports, so that both are looking like this, both the shape, it is almost parabolic in shape. And here there are two sags are possible. One is from the lowest tower to the lowest point, the sag is called S1. From the highest tower to the lowest point, the sag is called S2, and the difference between these S and S1 and S2 is called as H. H you can able to find. H is the difference in level between two sag, then you can able to find it. And here in two unequal level of supports, we assume some of the variables like x1 is the distance from the lowest tower to the lowest point of the conductor, and x2 is the distance between lowest point of the conductor to the highest tower, and the total line length is L. These are the assumptions we made. Okay. Coming to the line sag. While erecting a transmission line, an overhead line, this is also once again only possible or only way you have to calculate in an overhead line. It is not applicable for cables. While erecting an overhead line, it is very important that the conductors are under safe tension. Why we have to particularly calculate the sag mean? Sometimes if you stretch the conductor to reduce the sag or to reduce the amount of conductors which is required for a particular transmission line overall length, if you stretch the conductor between that, the length or the sag will be less, but the tension will be more. Sag and tension are inversely proportional. Sag and tension are inversely proportional. So that what happens in the sense, sag, lesser the sag, more the tension. And if you allow more sag, suppose if I want to keep it as more safer side, if I go for more sag, I am not worried about the cost of the material. If you give more sag over there, so that the tension will be less, and at the same instant of time, it will be the distance between the lowest point of the conductor to the ground level may be decreased. That also we have taken. There should be a minimum clearance between the lowest point of the conductor to the ground level. Yeah, these things you have to take. Yeah, this is a representation of tension. If you stress it, tangentially there is a force acting from the mid of the portion, that is called the tangential force, and those things we are going to calculate. So the simple definition of sag is the difference in level between points of supports and the lowest point of the conductor is called sag. Yeah. Just sag and tension calculations. This is for equal level of supports. When supports are at equal level, A and B are, as I said earlier, A and B are the equal supports, and the lowest point is O. We assume that there is a small portion P. P is operating point, where at that point there are two forces are acting. One act vertically, other one act horizontally. The vertical force is the weight. W into x is the vertical force which is acting at a distance of x by 2, and there is a tangential force which is acting tangentially at the distance of y from the operating point P. So with this, if you calculate that, the corresponding sag is WL square by 80, where L is the total length of the span, T is the tension of the conductor. By considering all the forces, see, if you see the expression, how we are getting the expression, since I am equating both the forces, the vertical downward force and the horizontal force at one instant of time, both should be equal. That is why Ty is equal to Wx into x by 2. If you substitute there, then you can find x is equal to L by 2 over there. Then the corresponding value of sag is WL square by 80. This is the formula. When supports are at unequal level, we have to calculate it. I said that there are two distances we assume, one is x1, other is x2. Our aim is to find x1 and x2, and the general formula, whether it is equal level or unequal level, the general formula is Wx square by 2t. If we substitute x is equal to L by 2, because in equal distances, the value of x means the distance between the support level to the lowest point of the conductor. In equal level, it is L by 2. That is why if you substitute L by 2 there, it is WL square by 80. That is the equal level. In unequal level supports, you have to find the value of x1 and x2 because both are different. In that case, if you find the value of x1 by x2, there are two conditions over here also. You find the sag at different level, then h is equal to s2 minus s1, that is already known. You substitute there, there is another equation called x1 plus x2 is equal to L. Substitute there and find the value of x1. We have two expressions, one is for x1, other is x2. Using this, we can able to find the distances. When x1 is known, you substitute in the general formula Wx1 square by 2t, so that you can able to find it. So that is about the sag. So to find the sag, first you have to see that whether your supports are at equal or unequal level. Accordingly, you have to choose the category. Okay, that is a conventional way of doing the thing. But practically, if you go and implement a transmission line, the force which we consider for calculation is only the vertical force due to weight, and the tension due to its own self-weight. But is it the case in the practical system? No, because due to the wind blowing, sometime it will get tilted, and that is called a slant sag. There are some cases where even in western countries or even in our northern part of our country, there are some ice coating over the transmission line, so that the total weight will increase. You see that the diameter of the conductor, you see the diagram, D is the diameter of the conductor, T is the thickness of the ice which is formed, so that the effective diameter is getting increased by D plus 2T. And the entire area is subjected to wind force. So if that is the case, once again your formula is getting modified slightly. See, this is the normal weight, W plus Wi is due to ice formation, and your wind force, due to that also your horizontal force is different, so that the total weight is Wt. So Wt is W plus Wi whole square plus WW whole square. Using this formula, you have to find the weight. Since there is a change in weight, once again go back to the formula. S is equal to Wx square by 2t. Your total weight is different. That is why everything is getting different. So that is called the slant sag, which is vertical sag by cos theta. That will give you. To find the tension, I always saying that there is a tension which is acting tangentially. How to find the tension? Which is the relation between working stress multiplied by conductor area. It is based on the size of the area. Otherwise, using the ultimate strength by safety factor, you can find the working stress, and the conductor area is given by the manufacturer itself. You can able to find. Yes, these are the various numericals based on sag that we are going to see. Here. Next. What are the various types of conductors? Because if you go for a mechanical design, first thing you have to see about choosing of material. Okay, for choosing the material and what are the various types of conductors which is available, and what are the various parameters which you have to see while choosing the conductor material. When the conductors are used in the transmission line, nowadays most of the cases we have ACSR conductor only, aluminum cold steel reinforced conductors only we are using. So for this, they should have low weight. They should have high tensile and fatigue strength. They must have high conductivity. They should have low coefficient of expansion, low corona loss. They should have less resistance and low cost. These are the factors you have to see while choosing the material. Yeah. Then, the advantage of using aluminum. I said that the ACSR is a conductor. Why we go for aluminum? If you go for aluminum, cost-wise it is less. Our ultimate aim is how to reduce the cost of the entire transmission line. In that case, majority of the cost is going for selecting the material of the conductor. If you replace this with a copper material, even though the conductivity is more, because of its cost, what will mean the overall cost of the transmission line is increased by 30 to 40%. So that is why we have to go for low cost. That's why low cost material is aluminum is one of the low cost material. Less resistance and corona loss, less weight. That is an advantage of aluminum. Advantage of aluminum is not only the cost, the total weight of the aluminum is less, so that the amount of support which you need to support the entire transmission line cost is also reduced. So several conductors which are made up of aluminums are all aluminum conductors is said to be AAC. Triple AC is called all aluminum alloy conductor. ACSR, that is a conductor which is almost we are using. Aluminum conductor with steel reinforced. ACAR is the aluminum conductor with alloy reinforced. So these are the different type of conductors which you are using. Yes, you can see that ACSR. Why ACSR? In the sense, even though the weight of the aluminum is less, the amount of the weight of the aluminum is less, not inside the tensile strength. The tensile strength of the aluminum is poor. Due to that, what happens is if you pass some amount of current, due to heat, it will get elongated, and due to cold, it may be getting contrasted. So to overcome these things or to improve the tensile strength, what we are doing is we have to go for imposing the steel inside the aluminum conductor. So aluminum are the present outside, and you have to put the steel strands. These are all called the strands which are present inside, so that the overall conductor tensile strength is increased. Okay. So ACSR conductors are commonly used as they have following advantage due to high mechanical strength, and the sag is small. So that is what we have to go for. They have low corona loss. Skin effect is less. We didn't know about the skin effect so far. What is skin effect in the sense? If you take a conductor, if you replace these conductors with a solid conductor, most of the time the tendency of the current is concentrated at the surface of the conductor only. Due to that, we are not replacing the effective area. That is one case. And also, most of the time, the outer strands is getting, or outer parts is getting punctured. So that is called skin effect. To overcome that, only we have to go for standard conductor. Even that standard conductor nowadays is replaced with hollow pipes also. That is to reduce the skin effect. All aluminum conductors, the conductors made from aluminum alloy are suitable in urban areas as they provide better tensile strength and conductivity. These alloys are known with different names in various countries. Some of these alloys are costly as they are heat treated. Okay, aluminum conductor with alloy reinforcements. This is also a type of aluminum product, but we are using only ACSR conductors. Then coming to the line supports. Once again, before choosing the line supports, we have to see what are the various properties. Based on that, we have to choose it. The line supports are, it should have high mechanical strength, high mechanical strength, light in weight, cheap in cost, and economical to maintain, longer life, easy accessibility because we have to erect the transmission line even in the hilly areas also. So transportation, the weight of the entire the support is less, then it is easy to transmit and handle. So that is it. The earlier days we started with wooden poles, then that is replaced with steel poles. Nowadays we are using RCC poles up to 33 kV distribution, primary distribution, and after that we are using steel poles. Yeah, wooden poles. Even though we are not using, just to know about what are the how the historical development of pole structures. The wooden pole, they are made up of seasonal woods and are suitable for lines of moderate cross-section area. The main problem of these wooden pole is you have to regularly maintain that. That is the main area, main drawback of this. Comparatively, lifetime is smaller, cannot be used more than 20 kV, less mechanical strength. Then we went for steel poles. Steel poles are often used as substitute for a wooden pole. They possess greater mechanical strength, longer life, and permit longer span to be used. Such poles are generally used for distribution purposes. Here also corrosion problem will be there in steel poles. So that is why we go for RCC poles, reinforced cement concrete poles. This reinforced concrete poles have become very popular as line conductor basically. Wherever you are going across the road, definitely you can come across these RCC poles. So that's why I'm saying starting from 230 volt single phase distribution, 415 volt 3-phase distribution, 11 kV primary, 33 kV primary distribution. Up to that we are using this RCC pole. Beyond 33 kV, starting from 66 kV, 110, then 400 kV, 765, 1200, everywhere we have to go for steel tower. Accordingly, the height of the tower will be. Yeah, these are some of the diagrams. You can see that steel towers where there are. These are called suspension insulators that we didn't touch about the insulators. These are the various insulators which are used in the line. The first diagram is 110 kV span at 320 meter for single cycle. Second one is for 220 kV span, same span of 320 meter, but there are double circuit. You can see that there are 6 conductors present. Then, how to reduce or how to optimally choose the size of the conductor? That's the next point. The economic choice of conductor is based on Kelvin's law. What Kelvin's law state is, see, whenever your annual charge on the capital outlay and annual cost of energy wasted is meeting at a particular point, that is the operating point where the cross section of the conductor you have to choose. So that is a statement given by Kelvin's law. There are some physical, many drawbacks are there in this Kelvin's law in the practical implementation also. Depreciation, the decrease in the value of the power plant, equipment and buildings of the everything is called depreciation. Due to depreciation, even if you are designing a plant for 1 ton, for example, there is a plant which is generating 200 megawatt of power. It may be a 10 years old plant. If you go and measure the maximum generation capacity of that, it may generate only 180 or 190 megawatt because of these depreciation. So aging is factors of this. So the annual charge, how to find these two? To find the annual charge, there is P1 plus P2A. Using this expression, you have to find what is the annual charge, where P1 and P2 are the constant, and A is the area of cross section of the conductor. Annual cost on energy wastage, that is P3 by A, because area of cross section is inversely proportional to resistance. Because the resistance, based on the resistance, only the annual cost is varying. That is very yes. If you find the total annual cost, if you add these two costs, you are getting P1 plus P2A plus P3A by A. To find the effective cross section, differentiate this with respect to the area by A, and you are getting a condition that P2A equal to P3 by A. According to Kelvin's law of statement, whenever that variable part of the annual charge is equal to annual cost of the energy wasted, at that point, whatever the area of cross section you are getting, that is the effective area. But sometime if you choose that area and if you go and see the current capacity of that, maybe you are not meeting the requirement. So that is the main drawback of Kelvin's law. So once again, the numericals were based on the Kelvin's law. Thank you. Yes. So next unit we are going to see about the insulators. So far we discussed about what are the various supports which are there, what are the various types of conductors which you are using for the transmission lines, etc. So now coming to the insulators. These insulators are different from whatever insulation which you are using. These insulators will supports or arrest the leakage current from the conductor to the ground. Okay. And these are all sometimes called as line insulators. And once again, we have to see what are the various properties of the insulator materials, then go for the types of the material. Coming to the various types of insulators which we are using, the properties are high, it should be high mechanical strength, high electrical resistance, high relative permittivity. The insulator material should not be porous. These are the various properties before choosing the insulation material you have to see. And the most common material which we have for using the line insulators are porcelain, graphite, kaolin, feldspar and quartz. These are the various materials which we are using for manufacturing the insulators. And the various types of insulators. There are 4 types of insulators: pin insulator, suspension insulator, strain insulator and shackle insulator. There are 4 types of insulators. One is pin, suspension, strain and shackle insulators. Coming to the pin type of insulators, these type of insulators, you can see the diagram how it is looking. There is a galvanized steel pin at the bottom of it, so where we have to go and fix it in the transmission line, and your conductor is at the top. You can notice here the conductor is present at the top of the conductor, top of the insulators, and this pin type insulator is used up to 33 kV. That means in primary distribution, if the voltage is 33 kV, there by increasing the number of petticoats, we can able to use it for up to 33 kV. Okay, that is pin type insulation. And mostly starting from 230 volt, 450 volt supply, then 11 kV, 20 kV, all these voltage levels we are using this pin type insulator. The next one is the suspension insulator, where you can see all these steel towers. Wherever you are seeing steel towers, there definitely there is a suspension insulator. If the voltage level is more than 33 kV, there you have to go for suspension. The entire thing is called a string. There is a conductor at the bottom. Each and every disc is capable of withstanding 11 kV of supply. If it is a 66 kV transmission line, there are 6 discs are there. So each disc is 11. So there are 6 discs are there. 6 into 11, 66 kV are there. That is about the suspension type insulator. And come to the strain insulator. Wherever the tension of the conductor is more, if you feel that, may probably in a street corners where at the right angle we have to change the position of the distribution line or transmission line, or if there is a road crossing where you can't able to, mostly the rule is you have to exactly perpendicular to the road, you have to cross the wire. If there it is not possible, there you have to go for strain insulators. The same kind of suspension string, if you use it in a horizontal position, then it is called as strain insulators. So the name itself, you can understand that these strain insulators are used to reduce the strain on the conductor. Shackle insulator, they are frequently used for low voltage distribution. Probably these are all called as strain insulators sometimes. If you put a stray between the RCC pole to the ground, to avoid the leakage of current through that, because it is made up of once again the conductor material, there is a stray insulators which is there in between the iron pole or iron clad to the ground. There you have to go for this kind of insulators. So what are the possibilities for failure of insulator? That also you have to see. The electrical breakdown of the insulator can occur either flashover or puncture. In flashover, an arc occurs between the line conductors and the insulator pin, and the discharge jumps across the air gaps. In case of puncture, the discharge occurs from conductor to pin to the body of the insulator. When such breakdown is involved, the insulator is permanently destroyed. See, initially during manufacturing itself, there is a small crack, it will prolong, and then due to high stress, it may get punctured. Or otherwise, there may be some dust particle deposited over the insulator material. That also will, due to aging, it may cause some failure. So the causes of there is a huge arcing from the conductor to the iron clad, etc. So that safety factor you have to ensure. So the puncture strength may flash over. You can see that there are 3 petticoats are there. There is a cross arm. There is a possibility of huge arcing. If it is getting punctured, then there may be arcing that will permanently damage the conductor. Yes, that is a very string. And these are the, see, if you use the suspension insulator, there you have to find whether the voltage is equally distributed among all the discs. Let us say, see the first diagram. There are 3 discs are there, each and every discs are mentioned over there. And there are 3 different voltages mentioned, V1, V2, V3. And these voltages V1, V2, V3 all should be equal, but practically is it same? No, it is not equal. So this is because if you only self capacitance are there, C is the second diagram, we can see that there is only self capacitance are there in the picture. If only self capacitance is there, then equally the voltages are distributed. But there is a virtual capacitance between the line supports the midpoint of the conductor, that will form a shunt capacitance called C1. So that due to that C1 or shunt capacitance, what happens means the uniformity of the voltage distribution is not there. So that if the uniformity is there, then the efficiency should be more. If I am saying that the string efficiency is 100%, that means V1 equal to V2 equal to V3. But most of the time, the value of V3 is more than V2 and V2 is more than V1. This is because of the conductor is at the bottom of the entire string. So this is important to find the string efficiency, particularly for a string if there is a suspension insulator. The formula to find the string efficiency is voltage across the string by N. N means the number of discs multiplied by voltage across the disc near to the conductor, where in our diagram it is V3. That is why it is written as V by N into V3 will be the efficiency of the string efficiency. So this is simple calculation to understand the string efficiency using Kirchhoff's current law. First apply Kirchhoff's current law and then you have to write it. So I1 is equal to I1 plus I1. So from there you have to find the current equations, convert each and every equation into voltages, and then you have to frame the equations for different voltages in terms of K. Okay. So K, where K is the relation between C1 and C. C1 equal to K times C. So that is why it is called a string efficiency. And substitute here and then find the corresponding value. Okay. So what are with the disk? We need to find the string efficiency here by how to improve the string efficiency. We know that the string efficiency is poor because of unequal voltage distribution. How to make the system to be equal, or voltage distribution should be equal in the sense by using longer cross-arm. I can go for longer cross-arm so that the effective of that shunt capacitance is reduced, so that if the shunt capacitance effect is reducing, the K is reducing, so the effect is also reducing. Like that we can able to do it. That is by using longer cross-arm by grading of insulator. That means for different insulator, different position, we can go for different gradings, so that amount of capacitance will be uniform, so the voltage will be same. So by using these technologies, we can able to improve the string efficiency. But the third and practical one which is there in the system is using guard ring. Guard ring is a ring which is nothing but a conductor which is connected one end to the conductor, other end to the atmosphere. So this will form another capacitance, so that if both the shunt capacitance are matching, for both the C1 and C3 and C1 and C2 are cancelled, so that the uniformity of the supports will be there. And otherwise, I can say that C1 is cancelling C3, the effect of C1 is cancelling under C2, so that only self capacitance is there in the system, and that way the uniformity no voltage distribution. So these are some of the numericals based on the distribution of power. Yes. Next, coming to the underground cables. In the underground cable, why we go for? So far we discussed about overhead line system only. Coming to the underground system, underground cable is comparatively high cost when compared to overhead line. You don't have to compare its advantage and disadvantage, you always compare with an overhead line. In an underground cable system, better appearance and less interference is there. But here no better appearances are no better in the sense if you see some of the transmission line, there are many lines are connected, many service lines are connected. The divided unit has no appearances or no better appearances. Cable lines are designed to be underground or underground water. The conductors are insulated from one another. It does not require insulation. So that is the cost of underground cable is somewhat more when compared to this. Cable lines are usually more expensive. Here it is less expensive. They have a capacitance problem. Here there is no capacitance problem. So this is a diagram to understand the cross section of an underground cable, where you can see that the conductors are there. It is surrounded by a conductor shield. There are cross-linked poly insulations. Over there is an insulation shield. There are some concealed wires inside to give mechanical protection. And then there is an outer serving layers also there. These are the various layers. These are different cable you can see. Coming to the construction of the cable, you can see that there are three conductors. It may be copper or aluminum. It is supported with it is surrounded with a paper insulation. Then there is a lead shield. There is a bedding layer. Bedding layer is a layer which is made up of some cotton or cloth material to give cushion effect, so that this armoring. Armoring is a metallic tape which will injure the lead sheet or even the paper insulation or sometimes the core itself. To avoid that, there is a bedding, and to cover the entire layer, we have to have serving layer. Fibers is made up of fibrous material to protect harmony of the atmospheric conditions. And there are some effects like capacitance. Even though corona effects are not there, there are some effects called capacitance of a single phase overhead line you have to take care. Direct stress in your transmission line, there is a cable you have to take care. Then grading of cable. Here also grading in the sense, we know that there are some insulation materials over the conductors. In order to make the stress uniform in that insulation, we have to go for grading. This grading is different from the grading of insulator. And there are two types of gradings are possible. One is capacitance grading, another is intersheet grading. In capacitance grading, we go for different material. You see that there are, this is the insulator, there are three materials, epsilon 1, epsilon 2, epsilon 3. Each and everything is made up of three different insulation materials, so that different permittivity and so uniformity in the distribution. So the potential gradient is uniformly distributed in the each and every point. Yeah, next one is the intersheet grading. The problem with capacitance grading is there we can't able to use our manufacturing problem will be there, so that we can't able to go for three different layers of material. So use the same material of epsilon permittivity. In between that, we have to insert some sheath which is made up of some conducting one, which is maintaining at different voltage. You can see that there are intersheath 1 and 2, which will serve the same purpose of the capacitance grading. These are some of the numericals based on that we have seen. Thank you. Good morning, friends. So today, in this lecture, 1 hour of lecture, I am going to talk about how to model various transmission lines in power systems. Coming to the classifications of transmission line, a transmission line has classified into three models: short, medium, and long transmission line. How to classify these short, medium, and long transmission line in the sense? Short transmission line is a line where the distance of the transmission line is 50 km and the working voltage is the range of 20 kV. So what I can say is, in a short transmission line, the line which is less than 50 km and the working voltage, if it is line to line, I am saying 20 kV, then it is coming under the model of short transmission line. The next one is a medium transmission line. In medium transmission line, we have between 20 to 100 kV. We can say that it is a medium transmission line, and the line length is up to 150 km. 50 to 150 km, we can say it as medium transmission line. The next type of model is called as a long transmission line, where the working voltage is more than 100 kV and the line length is more than 150 km. These are the various types of classifications of a transmission line based on the model. Okay. So how it is making the difference in the sense, in short transmission line, there are three parameters are there in transmission line. You know that: resistance, inductance, and capacitance. Among these three parameters, how we are going to assume, like RLC, whether it is going to be lumped in nature or distributed in nature. Practically speaking, all these three are in distributed way, but here what we are considering is, in short transmission line, we are neglecting the effect of capacitance. Why we are neglecting the effect of capacitance means, in short transmission line, the dominance of capacitance when compared to resistance and inductance is very less. Okay, that is the reason we have to omit the effect in the short transmission line. Coming to the medium transmission line, here we are going to consider all the three parameters: resistance, inductance, and capacitance. But all the three are lumped parameters. Instead of distributed in nature, we consider it as a lumped parameter. In long transmission line, here also all the three parameters are considered, but the main difference is, in long transmission line, we have RLC, which are distributed, which is the same as that of the real-time system. How the real-time resistance, inductance, and capacitance are distributed, the same way we have considered. So then that way there are three model of transmission line based on the line length and working voltage. Yeah. In order to conclude all those things, in a short transmission line, if you see that, that's why I discussed about that. It is less than 100 kV and the distance is less than 50 km. Both the resistance and inductance are lumped parameters. We neglect the effect of capacitance. All these modeling, the purpose of doing this model is to find the performance of the transmission. Performance in the sense, there are two things are there. One is the efficiency, other is the voltage regulation. Even by neglecting the effect of capacitance, if we calculate the efficiency of voltage regulation in short and medium transmission, short transmission line, there is no huge change in the corresponding number which you are getting. That is why we are neglecting that. Not easy the calculation. That's it. In medium transmission line, as we discussed, 20 to 100 kV is the working voltage, and the line length is between 50 to 150 kilometer. So that is why here also we consider all the three: resistance, inductance, and capacitance. The main thing is all the three parameters are lumped. So if you go and see the calculation practical value with this, there is a slight mismatch between the practical value and the theoretical computation which you are doing with these assumptions. So to overcome that, we have to go for long transmission line. Long transmission line is a line where the distance is more than 150 km. In the sense, the distance between the sending end to receiving end is more than 150 km, and the working voltage is more than 100 kV. Then it is called as a long transmission line. In long transmission line, if you assume all the three parameters to be lumped in nature, so what happens means, because of that, the error which is developed in the transmission line or the performance is very more. That is why you can't able to do that. In long transmission line, there is a method called rigorous method. Using that method, we have to find the voltage regulation and efficiency. There is a three way of classifications. So performance of the transmission line. In all these three cases, as I said, there are two things we have to do. One is the voltage regulation, other one is the efficiency of the transmission line. See, here, to find the voltage regulation, the general formula which you are using in your transformer, etc., it is Vs minus Vr by Vr into 100, where Vs is the sending end voltage, Vr is the receiving end voltage, and Vr is the Vr divided by Vr will be the corresponding voltage regulation. And the tolerance limit should be within plus or minus 5%. The voltage regulation which you considered should be within plus or minus 5%. That is the thing we have to maintain. Then coming to the transmission efficiency, this is also important. We are trying for 100% of efficiency, but practically it is not feasible to get or possible to get 100% efficiency. So in that case, what we are going to do is to find the transmission efficiency. You know the here Vs, Is, and cos phi s are the sending end parameters. Vr, Ir, and cos phi r are the receiving end parameters. So receiving end power by sending end power will give you the efficiency of the transmission line. Okay. So as much as possible, we are trying to improve the efficiency more than 90-95% by adding some of the components like fax devices, etc. So these two we are going to discuss. What is how to find the voltage regulation, how to find the transmission efficiency for different case of model. Yes. Yeah. First one is the a short transmission line. In short transmission lines, we assume that all the transmission lines are analyzed in the per phase model. That means, since it is a balanced system, we assume that the system is balanced. Here, we consider that all these models, when discussing all the model short, medium, and long transmission line, the line which is considered is a per phase model. So here, if you see that there is a sending end voltage, VR represents the receiving end voltage. The lumped parameter, the resistance and inductive reactance are shown here. That is the total resistance, total inductive reactance, and the current which is at the sending end is Is. Current at the receiving end is IR. In this case, both are equal because we neglect the effect of capacitance. There is no parallel branch or shunt branch. That is why Is is equal to IR over here. So remaining things are there. Then cos pi r is the receiving end power factor based on what type of load we have connected. Based on that, it is going to be. Yes. So in order to represent all these parameters, like sending end and receiving end parameters, we need to draw the phasor diagram representation normally. So that is why by taking VR as reference, if you see the graph, by taking VR as reference, to reach Vs, to reach the sending end voltage, there are two drops are there. One is IR, other one is IXL drop, where IR is the resistive drop. Is is equal to IR is equal to I, we assume. So that is there. Wherever the current is there, this current is always lagged by an angle of IR because most of the time the load which is connected to the transmission line is inductive in nature. That's why. So IR is there. With respect to this, exactly in parallel with this, you have to draw one line called IR. Since always the current is in phase with the resistance, that is why it is in phase. And from here 90 degree, you will draw IXL. That is another drop due to inductive reactance. In total, the drop is IZ. If you add this receiving voltage with respect to these two drops, that is your sending voltage. Okay. So that is IZ. Since we take VR as reference, it is VR plus J0. The current is always lagged by an angle of pi r. That is why I is I minus pi r, which is I into cos pi r minus J sin pi r. Z is the total impedance of the transmission line, which is R plus JXL. And Vs, VR plus I into Z will be Vs value. That's the vectorial addition of VR plus I into Z. So using this, you can able to find the value of Vs. So Vr is already known or determined, or we fix the value of Vr. With that, we can able to find the regulation, efficiency, or whatever thing you want to calculate. We can do that. Calculations. But actually, the system is a three-phase system. How to model that in a three-phase way? You can see that there are normally the transformer is of star connection. Then here the load is also we assume it to be a star connection. So there is a three lines are there, R and XL, RXL are the three transmission line which is connecting the sending end to the receiving end. Sending end may be the transformer, receiving end may be your load. In that way, the single line diagram of that is also shown. Once again, voltage regulation. Then after that, how to find the power. Since it's a single phase, we assume that the three-phase balance system is modeled as a single phase system. To find the power, that is the receiving end power, it is VR, IR, cos pi r. Here IR is equal to IS, that's why we return it as I. So I is P by VR cos pi r, and this P is the receiving end power. Okay. So like this, you can find the sending end power also. So two powers are known, or otherwise I can say that the output power is known, the losses is also calculated, you can easily find the efficiency of the line. Coming to the medium transmission line. In medium transmission line, already we discussed that the model is for the line length between 50 to 150 kilometer and the voltage between the range of 20 to 100 kV. So here all the three parameters are considered, resistance, inductance and capacitance are considered. All three parameters are lumped parameters, and there are three models. In medium transmission line itself, there are three possible models are available in the literature. One is the medium transmission, N condenser method, nominal T method, and nominal pi method. These are the three methods which we have. Now there is N condenser method, nominal T, and nominal pi method. Why it is N condenser method? The entire capacitance are considered at the end of the transmission line, or otherwise receiving end of the transmission line. That is why it is called as N condenser method. The second model is called nominal T model. If you see the equivalent circuit of the model, it is looking like T. That is why it is called nominal T model. Pi, once again, it is looking like a pi structure. That's why it is called as a pi model. Generally, in practice, in the transmission line, if you model, we use nominal pi model only. The reason is, in pi model, the entire capacitance is divided into one at the sending end, other one at the receiving end. That is why we go for nominal pi model. Okay. So we'll see one by one. Yeah, in N condenser method, as we discussed, resistance, inductive reactance, and capacitance, all the three are lumped in nature. The capacitance is at the end of the line, transmission line, so that is near to the load it is. Okay. So lumped parameters are X and C. If you see the sending end current, IS represents sending end current, IR represents the receiving end current, there is a capacitive current. The sending end current, there are two equations you have to write, one is for the voltage, other one is for the current. So the current equation is 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 equal to IR plus IC. The total current equation, sending end current is equal to IR plus IC, and Vs is equal to, the total voltage is Vs, is equal to VR, that is VR plus whatever be the drop in this corresponding R and XL, we can find the Vs value. Ultimately, in all these models, our aim is to find the regulation and efficiency in this. Okay, then condenser method. Here, once again, to draw the relation in terms of phasor diagram, you can see that similar to the previous case, short transmission line. Here also we consider VR as a reference. There are two currents, even three currents are there. The summation of IR plus IC. IR is the receiving end current, IC is the capacitance, shunt branch current. If you add these two, that is your IS. While drawing this, how to draw these current vectors in the sense? By taking VR as a reference, IR is lag by angle of IR. IR is lag by angle of IR. From here, the capacitive current is exactly 90 degrees from that. If you add these two, that is your sending end current. Okay? And the drop after VR, VR is there. If you see the phasor diagram here, VR is the voltage, the receiving end. The current which is flowing in this R and XL is IS. So that is why you can see that in parallel with IS, what you have to do is you have to draw ISR and ISX, ISXL.